In this lesson, we are going to talk about how intermolecular forces affect properties. How does a substance property depend on its intermolecular force? So the first thing that we need to remember is that intermolecular forces are the forces that hold molecules together. So let's say I had a few Erlenmeyer flasks. And in the first one, I had a solid. Let's say it was water. So water was frozen, like ice cubes. And then we had a flask of liquid water, and then we boiled it into a gas. So what we have to know for intermolecular forces is they hold the molecules together. So if I had all of these water molecules and they are in the solid state, those molecules are going to be held tightly together. As a liquid, the molecules are going to be a little bit more spread out, and as a gas, they're going to be very far spread out. So that means that the strength of the intermolecular force is much greater for a solid than it is for a gas. So there is a force that is holding these molecules together. The stronger the force, the tighter those molecules are going to get pulled together. So that will be an important thing to remember as we go through these properties. We saw in the last lecture that there may be multiple intermolecular forces acting on a molecule. Maybe it has London dispersion forces, dipole-dipole, and hydrogen bonding. So when we're looking at properties, the strongest intermolecular force will determine properties. The strongest intermolecular force will determine properties. The first property that we are going to talk about is boiling point. So first, what happens when something boils? When a substance boils, we're going from a liquid to a gas. The molecules get pulled further apart. Molecules go from being close together as a liquid to farther apart as a gas. We can see as a liquid, there's going to be an intermolecular force holding these molecules together. If we want to boil this liquid into a gas, those molecules need to be further apart, so that means that we are going to have to break those intermolecular forces. So that leads us to our first trend. The stronger the intermolecular force, the more difficult it is to separate the molecules. The more difficult it is to separate the molecules, the more heat energy is needed. So again, in order to go from a liquid to a gas, we need to separate those molecules. If we're separating those molecules, we need to break that intermolecular force. Well, the stronger the intermolecular force, the harder it is to break it, the more heat energy we're going to need. The stronger the intermolecular force, the higher the boiling point. The stronger the intermolecular force, the higher the boiling point. Similar to boiling point, let's talk about evaporation. When something evaporates, it changes from a liquid to a gas. Think about if you were to spill a little water on the table. Over time, you are not going to see that puddle of water anymore. It is going to evaporate. It turns into a gas. Well, this one is going to be very similar to boiling point, because boiling point is also going from a liquid to a gas. The stronger the intermolecular force, the harder it is to separate those liquid molecules into those gas molecules, which are farther apart. So we're going to notice the same trend. The stronger the intermolecular force, the harder it is for those molecules to separate, the harder it's going to be to evaporate. If we have a really strong intermolecular force, it's going to evaporate slower. If molecules have a strong intermolecular force, they want to stay together in that liquid state. It is going to take a lot of energy to get them to evaporate. The more energy it takes to evaporate, the longer it takes to evaporate. Strong intermolecular forces take a long time to evaporate. Molecules with weak intermolecular forces evaporate pretty quickly. The last property we're going to talk about for today, cohesion or surface tension. This is the resistance a liquid has to spread out. It does not want to increase its surface area. So think if you ever have seen like a drop of rain or some dew on like a blade of grass early in the morning, think of how that water kind of bubbles up. It is resisting spreading out. That's because it has a lot of surface tension or a high cohesion. The stronger the intermolecular force, the greater the surface tension that liquid will have. Again, intermolecular forces are the forces that are holding our molecules together. If we have a really strong intermolecular force, those molecules are going to be held tight together. You're going to see that liquid kind of bubble up like we see a drop of rain. If it has a very weak intermolecular force, you're going to see that it's going to spread out. Those molecules aren't held together as tightly, so they're going to have a weaker surface tension and you're going to see them spread out. So last thing that I want to do today is a few examples looking at these properties. Let's say we had 3 molecules, CH4, CH3OH and CH3Cl. We can start by drawing some Lewis structures. All right, so I'm going to ask a series of questions about these three molecules. So the first thing that we should do before we even attempt to answer any of these questions is to determine their strongest intermolecular force. So first, let's go through and figure out polarity. Look at your central atom. Everything attached to it is the same. It is completely symmetrical. This is nonpolar. Look at your central atom. Is everything attached to it the same? No. Hydrogen, 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 oxygen. Because this one is not symmetrical, it is going to be a polar molecule. Last one. Look at your central atom. Then look at its attachments. Hydrogen, 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 chlorine. Since all of those attachments are not the same, it is asymmetrical. This is a polar molecule. Next, determine intermolecular forces. Every single molecule has some London dispersion forces acting on it. If it is nonpolar, LDF is its only intermolecular force. If it is polar, it also has dipole-dipole. Lastly, look for sites of hydrogen bonding. If I had hydrogen bonding, hydrogen would be attached to either oxygen, nitrogen, or fluorine. Oxygen is attached to hydrogen. This middle one also has hydrogen bonding. We said if there are multiple intermolecular forces acting on a molecule, the strongest intermolecular force determines its properties. So for the first one, LDF is the only force, it's going to be the strongest. My molecule in the middle, hydrogen bonding, is the strongest of the three. Last one, dipole-dipole, is stronger than LDF. So now let's go through and answer some questions about properties. A. Rank in order of increasing boiling point. So let's think back to our trend. The stronger the intermolecular force, the greater the boiling point. So the weaker the intermolecular force, the lower the boiling point. So all we have to do is rank these in order of strength. Well, LDF is the weakest. That means CH4 would have the lowest boiling point. Next, in terms of strength, would be dipole-dipole. Hydrogen bonding is our strongest intermolecular force. Since that's the strongest intermolecular force, it would have the highest boiling point. So I'm ranking them from lowest to highest boiling point. B. Same three compounds. Which would evaporate first? Well, our trend for evaporation is the stronger the intermolecular force, the longer it takes to evaporate. If we have a really strong intermolecular force like hydrogen bonding, it's going to take a very long time to evaporate. Those strong forces are going to keep those molecules together in the liquid state. The weaker the intermolecular force, the faster it would evaporate. So which would evaporate first? We're looking for the weakest intermolecular force. Last one. Which would have the greatest cohesion? Cohesion, just think about it like sticking together. Which molecule is going to stick together the best? Again, intermolecular forces hold molecules together. The stronger the intermolecular force, the more those molecules are going to be stuck together. So if we're looking for the greatest cohesion, we're looking for which of these three molecules has the strongest intermolecular force. Of dipole-dipole, hydrogen bonding, in terms of London dispersion forces, hydrogen bonding and dipole-dipole, hydrogen bonding is the strongest. So CH3OH methanol is going to be the greatest cohesion. Stronger intermolecular force, the tighter those molecules are held together, so the greater the cohesion will be.